2013, and much in the spirit of the interdisciplinary nature of the research, which is done in soft matter physics in general, which was pointed out by Professor Zrucki in his historical lecture, I'll try to present very, humbly, what some kind of mathematics can do for you, and I hope I'll convince you that you need to be familiar with some mathematical tools in order to understand better what is happening in soft matter science. All right, let me start with the physical motivation. This is not going to be just a lecture on mathematics, but as I said, these mathematical tools will serve a purpose, and the purpose they serve is to understand better some general physical laws. And another title that I could have be given to this lecture would have been a lecture on entropic forces. This makes it a little bit more appealing, though maybe the focus of the lecture would not have been sufficiently highlighted. Entropic forces are is a generic term which indicates interactions that might drive phase transitions in addition to forces we are more accustomed to conceive, such as those which arise from interparticle interactions. And it has been recognized by many people, especially in the last, I would say, 20 years, that these forces might be the major players, especially in devising the supramolecular organization. So they do not only help understanding better what happens at the molecular level, but they could be of use in understanding how, for example, the organization of colloidal particles in ordered patterns could be achieved. And so this is a very short recap of what is our general understanding of a phase transition. Of course, everybody knows what F means here, it's just the free energy of the system. This is a very generic statement, and we say that a phase transition, such as condensation, for example, or any other ordering transition in soft matter or in any kind of condensed matter, actually arises as a result of this eternal competition between energy and entropy. There is a battle behind the scenes between internal energy and entropy, and the idea is that all transformations that we are interested in will certainly decrease the free energy, and this, of course, can be achieved by reducing the internal energy, of course, and at the same time we need to be careful in increasing the entropy. So, of course, imagine, for example, a usual condensation transition in which the temperature is reduced. This quantity T is the absolute temperature. It is decreased, but in order for the battle to be won, we need a decrease in energy, in internal energy, which, of course, must not be completely neutralized by the behavior of this term, because the temperature is reduced, meaning this quantity is increased, but it is necessary to have an increase in entropy in order for this difference to be reduced. So a reduction in temperature is needed, and at the same time an increase in entropy is needed in order for this battle to be won. All right, this is a very simple-minded explanation of what is going on in a transition, but let us look forward and let us consider, just for the sake of argument, a situation in which the internal energy does not depend on temperature. I've not made any predication in my previous comments on the variables that might influence those thermodynamics quantities. And now I assume that the temperature depends only on that, the internal energy depends only on temperature. There is no dependence on density. Suppose, for example, you have just a bunch of particles bumping one upon another. There is, of course, an internal energy due to the kinetic energy of these particles, which is fixed by temperature, but there is no other contribution coming to the internal energy depending, for example, on the density. All right, if we now apply the previous paradigm to this system, there is only one way to enforce at a given temperature to enforce phase transition. So U does not depends only on temperature. Suppose that your free variable is the density of the system, temperature is frozen, is fixed. U does not depend on temperature, so does not depend on density, depends only on temperature, so you have no way to affect this difference but by increasing entropy. So the idea is that in order to go from one state to another by changing only the density of the system, you needed to increase the entropy. So it means that if the entropy is increased, it means that the disorder, in a way, is increased. And so this is an ideal realization. It is a kind of contradiction in terms, but this is a remark made by Dan Frankel, who said in this very nice paper, almost 14 years ago, when he said, well, look, there is an ideal system in which what I am trying to describe would take place, and it is a system of particles which do not interact at all. So they are just rigid particles that wander around, and they interact only via the law of impenetrability. One particle cannot penetrate into the other, and so there is no attraction, no repulsion whatsoever between them, but the interaction that comes from what is called hardcore interaction, which means that this is an ideal system, ideal in many respects, because it can be properly realized on a computer, but it is an ideal system in which in which its internal energy depends only on temperature, and there is no further dependence on density. All right, so can we conceive, for systems of this sort, can we conceive a kind of condensation transition? And well, this idea is actually goes back to the work of Onsager, who did actually predict that an ordering transition would occur in a system of slender rods that would interact precisely in this fashion. And his prediction was based on, we'll come back to this in a minute, but his prediction was based on a mechanism which would predict an ordering transition as soon as the critical value of the density of the system is increased. And what happens to these rods, according to the computation made by Onsager, is that if you increase the density of the system above a critical value, then all of a sudden the orientation of the particles, which in the low density limit would be completely random in space, all of a sudden becomes oriented in one direction. So the orientation gets aligned, and all these rods go from the random alignment to a precise direction alignment, which actually could be in everywhere oriented in space. So, well, just to make this more precise, you go from a random state to a state which is ordered. On average, these rods are oriented in one direction, but the direction which is picked up by the ordering is arbitrary. It could be any direction in space. So there is some kind of arbitrariness left also in the ordered state, but the molecules, these are, if you want to think of molecules in this state, are ordered. You don't know which direction will be picked up, but certainly the system is ordered in the high density regime. All right, then we should, and this was a prediction. It would be nice to go into the details of this seminal paper. I wish just to make just a small comment following Professor Drukin's remarks on the history of liquid crystals, well, this I think is the first theoretical advancement in the theory of liquid crystals. And there are, I mean, in my mind, at least, there are three important dates in the history of the theory of liquid crystals that should be remembered. One is this, 1949. Another is 1958. And two important things happened in 1958. There was almost, 9 years after this seminal paper by Unsager. And there was the first continuum theory for the equilibrium proposed of liquid crystals proposed by Sir Frank. And at the same year, there was this famous Mayer-Zaupe theory, which was a mean field theory that predicted, again, on completely different basis, the transition for thermotropic liquid crystals. In that case, in their theory, the variable that induced transition was temperature, and it was not density. And 10 years later, 1958, the first dynamical theory, the famous Erickson-Leslie theory, was published. So there are, these three pillars, and the first one is Unsager's. And Unsager simply predicted this transition based on an argument which would be interesting to examine, but I don't have time, because it is a nice example in which a minimum problem is tackled by reducing the space of all possible states to a number which is infinitely dimensioned to a finite dimension subspace. So in this sense, I would say that Unsager, since it was not properly, the free energy was not properly minimized, left some open doubts on the validity of the conclusion itself. And actually, there was a question that I had prepared for you, and one could really seriously question whether the ordering transition that was predicted by Unsager indeed complies with the principle of minimum free energy. And the reason is very simple, because I said, and properly said, that this is an ordering transition. In this ordering transition, the entropy is reduced. So how come that, coming back to our previous slide, it is a situation in which the temperature is not changed, U depends only on temperature, S is decreased because there is more order in the aligned state, and yet the energy is minimized. So maybe there is a mistake in Unsager's derivation, and as I said, if you look carefully at the derivation of Unsager's paper, you might come to doubt it, because it is not an ordering minimization, it is a minimization on a restricted subspace. So this was the question, of course, and of course there are two possible answers. The first is, well, no, this is wrong. The entropy is not decreased. The entropy is not decreased, and the energy remains unchanged, so the free energy cannot be reduced. And so one reaction to this remark would be, I'm not going to buy it, because it doesn't comply with the basic principle of thermodynamics, which prescribes the free energy to be reduced in the transition. But of course, there is another suspicion that might arise, and the suspicion is, okay, it is correct. Unsager's prediction is well-rooted, but of course, I am missing something. There must be some hidden source of disorder which I have not yet considered in the picture. Of course, the correct answer, I would have asked this question, but the clickers do not work today, so I needed to pose a question and answer them at the same time. Of course, the answer is, correct answer is B. There is a hidden source of disorder, though this sounds as a kind of vague and political answer to the question. This, for once, happens to be the correct answer. And the correct answer is, indeed, the free energy minimum is not lost. The free energy is minimized. And indeed, this ordering transition, which apparently reduces the disorder and so increases the order is indeed such that the total disorder is increased. And the reason is that in considering the source of order and disorder in this transition, you should look at all possible degrees of freedom of your rods. It is true, the orientational degree of freedom have been reduced in the ordering transition. But think of for a moment what happens to slender rods, which are more oriented in one direction than randomly distributed around. They can glide more easily one upon the other. So in a way, they can be more disordered in space. They are more ordered in the orientational degrees of freedom, but they can be, not necessarily are, but they can be more disordered in the positional degrees of freedom. So there is larger mobility. And this is precisely what happens to rods, and this is precisely what Onsager was considering in his paper. Slender rods. Slenderness is important because there is this subtle balance between the increase in orientational order and the decrease in positional order. Conceptually, if overall the degree of disorder is increased, then there is a chance that the ordering transition, ordering in the orientation degrees of freedom takes place, notwithstanding the fact that apparently the order in orientation is increased. All right, of course, what does it mean for us? And this is the end of my long introduction. Well, this means that there is an important measure of disorder that we need to keep in mind in order to understand these orientationally ordered transitions. And this is just in terms of accessible volume. If I want to increase the positional disorder, I need to think of a transition in which more volume is made accessible to the particles. And if more volume is made accessible to the particles, it means that I need to maximize the volume accessible to them. But to maximize the volume accessible to them, I needed to minimize the volume that they cannot access. And so this is one possible, among many others, motivation of why the excluded volume of interacting particles is so important, because in order to ensure that an ordering transition happens when I increase the density with no temperature change, I need to be sure that I understand what is the mechanism that makes more space available. And so I need to be sure of what means I have in my hands to reduce the excluded volume. And so this is the reason why excluded volume is so important in ordering transitions, because it is a measure of positional disorder. Minimizing the excluded volume means maximizing the accessible volume, and so it makes your hopes of getting an ordering transition larger. Of course, computations at the end of the day must be done, and people know how to do them, especially people who do simulations know precisely how to do these computations, but there is no hope if you know that your shape, the shape of the things you are playing with, is such that it is very difficult to maximize the accessible volume. There is no hope to get an ordering transition. So knowing the excluded volume of two shapes, two rigid shapes, is crucial. So how do we do? Well, the mathematics, this interesting for convex bodies, at least, there is very nice and classical theory which was put forward by Brun and Minkowski. Well, this is a nice story. Actually, I don't have much time, so I need to rush, but Brun paper, actually, this is not a paper, this is a dissertation, which was published in 1987. Brun was Minkowski's student, the theory, Brun-Minkowski, is based on Brun's dissertation, which was published in 1987, and then the colossal paper published several years later by Minkowski in 1903. It is a huge paper, 120 pages in Annalen Mathematik, and of course the contents is essentially the same, so nobody knows, of course, how to share the credits about between these two authors. And so this is the reason why I call it the Brun-Minkowski theory. Well, this is a very deep theory, though it is limited to convex bodies for reasons that I hope to be able to explore in more details towards the end of my lecture. Conceptually, it is a result of merging together two notions. One notion is the notion of vector addition in the translation space associated with every Euclidean space. Euclidean space is characterized by actions on it, and one of the actions on it is translating point into another point, and this is called a vector in the common language. And so this linear structure, which is hidden in the vector structure, is merged with the notion of volume, which is properly introduced in an Euclidean space. This is a very general theory. It works in any space dimension. Of course, we are interested only in three-dimensional bodies, even in two-dimensional bodies, but the theory is completely general. All right, everybody knows what a convex body is. I don't think I needed to go into any further details. This is the generic picture which arises in our mind when we speak about convexity. It is a novaloid, and it has a property that if I pick up any 2 points in the system, the straight segment joining them, and I need for this the Euclidean structure in order to be able to join a segment between the 2 points, has to be completely contained in the body. All right, we also say that it is strictly convex if the boundary does not contain any segment. For example, a cylinder is not strictly convex, a cone is not strictly convex, and ellipsoid is strictly convex. And we also need the notion of smooth boundaries, and sometimes K plus is the symbol that denotes the collection, the class of all strictly convex bodies with smooth boundaries. And the fact that the boundary is smooth and the body is convex entails that all principal curvatures of the boundary are strictly positive, and this is the reason why there is a plus sign on top of the symbol. So this is Minkowski's idea. We endow the class of all convex bodies with a notion of addition. So what we do is simply learn how to add one body to another body. And so we construct the Minkowski sum, which is the result of this addition. Well, it is simply the addition of two convex bodies is simply given by summing together all vectors that identify points in each body. Of course, a graph is much better to illustrate this, but before just showing a graph, I would like also to point out that you could also introduce the notion of scalar multiplication in this set of convex bodies. What you do, you simply pick up an origin and you inflate or deflate your body by multiplying the vectors that identify the points in the body by a given scalar. Or mind that this scalar can also be negative, meaning that you can invert the body. For example, if lambda is -1, what you get is a central inverse of the body. So the idea is that you endow this class of convex bodies with two typical operations, which are those which we all learn in linear algebra. All right, this if you just type Minkowski addition on the web, there are many pictures that come out, And this is one that came out, which I found very, very illuminating. This is the origin. I pick up a point, and then I take all points in the green body, all points in the blue body, and I simply take the vector, which is obtained by simply adding up these vectors. So I take all points in the green, all points in the blue. I sum up all these vectors, and the result is this one. All right, this is sometimes very common in the engineering literature. It is another construction which is based precisely on the same idea. So you have a body here. You imagine that the two bodies have the same origin, and then you simply take the sum of all possible vectors that identify the bodies. And this is very often found in robotics papers, for example, because people who study the movement of robots needed to learn how the machine has to move in order to avoid obstacles. Of course, this is a completely equivalent problem to the one that we want to study. And these pictures are typical in robotics journals. All right, I had a very educational question here, and the question is Minkowski addition defined only for convex bodies? Yeah, but only 15 minutes are left. I'm sorry that I would, in the interest of time, I would. Well, the answer is, I think the answer is interesting. The answer is no. Of course, only by the definition I gave, convexity plays no role. So you could add together two bodies which are not convex. And this is the reason, actually, why this idea of Minkowski sum could be more relevant than I think it has so far realized in the study of entropic forces. But I'll come back to this. All right. Well, I just unveiled the answer to this other question. The definition, and this is something that in many books I think is a little bit overlooked. If you really go into details of the definition of the Minkowski sum, you realize that it is indeed a definition that depends on the choice of the origin. And but it is very interesting to remark that if you choose a different origin, then the result is another body, but the two bodies are related by translation. So the shape, and this is another important point, the shape is uniquely defined by the Minkowski addition, though the position in space is not defined by the definition properly. So it means that the shape is independent of the choice of the origin, but the specific body, and sometimes you are interested in locating the specific body which has been obtained by adding two bodies, depends on the choice of the origin. And overlooking this minor detail could be dangerous. All right. Well, these were considerations on the origin, on the role played by the origin, and this is another interesting question, another interesting issue that comes out of adding anybody with a multiple of the unit sphere, of the unit ball, which is again a ball of radius r. We call the spherobody, and spherobodies in this theory plays an important role. Essentially, it is obtained by adding to the body a ball of given radius, and it is interesting to see that this would be the shape obtained by summing in 2D by adding a circle, the green circle, to the blue triangle. Well, in other words, it is one way of just depositing a crust of radius r on top of the body. And the result is again a convex body, and it is a very nice way to round up corners and edges. So what you get at the end is another convex body, which is rather smooth, even if you started from a convex body which had corners, edges, and clasps. Well, the interesting point is you can endow the class of convex bodies with this notion of distance, and this distance is just built in terms of sphere bodies. It means that I call delta, I call the distance between two bodies the least crust, the least thickness of the crust, which allows me to realize that B1 is included in the sphere bodies of B2, and at the same time B2 is included in the sphere body of radius delta of B1. So it means essentially that I build a kind of neighborhood of a body V1 and of amplitude delta, and I want the body B2 to be within this neighborhood. But at the same time, I build the same neighborhood of body B2, and I want body B1 to be within that neighborhood. All right, if I take a delta very large, any two bodies would be such that one is included in the sphere body of the other. But as soon as I reduce, as I shrink the values of delta, there will be a minimum value of delta for which this double inclusion works. And I can prove that this, the lim-inf exists, well, this always exists, and the lim-inf of this sequence is precisely what I call the distance between these two bodies. Well, it is this Hausdorff topology is very rich because, well, there are a number of properties here that play an important role in building the mathematical structure of this class of sets. But the important point is that both polyhedra and strictly smooth convex bodies are dense in K. What does it mean? Well, mathematically, finding that one class is dense into another, it means that I can approximate. It is really important because it says that within this topology, I can approximate every convex body living in K with either polyhedra or very smooth bodies, which means that if I need to compute quantities of interest, I could compute them on the approximating subclass and then take an appropriate limit. So any convex body can always be approximated in this topology by either polyhedra or smooth bodies. All right, smooth bodies are very important because they can be parameterized by use of the inverse of the Gauss map. You can prove that if the body is in K plus, you can always introduce this radial mapping, which essentially attributes to the unit normal to any unit vector in S2. It attributes the point on the boundary of the body at which that normal is achieved. So the Gauss map usually is defined as a map that at a point on the boundary assigns the unit normal at that point. But for bodies in this smooth class, you can invert this mapping, and so you can actually represent the boundary of the body as an image of the boundary of the unit sphere. And this is very important because then you can prove that the Minkowski sum of two bodies is represented by the sum of the two radial mappings. So it gives you a kind of tool that enables you to compute the Minkowski sum as a result of the addition in the translation space of these two mappings. And the inverse body plays an important role in a minute. The inverse body is simply this is a central inversion. So when you take a body and you transform it into inverse, this is simply represented by this transformation on the radial map. All right, well, then Minkowski introduced a number of functionals, and the easiest of which is the integral mean curvature. You simply take the mean curvature on the boundary and you integrate it over, and then the surface area and the volume area. And all right, I need to skip all this. The important point is that all these functionals are continuous in the Hausdorff topology. And so this, again, is very important because it tells you that if you don't want to compute, or if you are not able to compute directly these functionals on a given convex body, you can compute it on the approximating nice sequence of bodies, and the value, the limiting value of these functionals on the approximating sequence is going to be the value of that functional on the limiting body. So this means that essentially you can introduce a kind of calculus in this class of sets. All right, I need to skip this. And these are important formulae for the sphere bodies. Sphere bodies in the theory are essential because they play the role of neighborhoods in a way. So you simply say that the neighborhood in this theory of a body is an appropriate sphere body. And then these formulae, which were derived by Minkowski in his paper, are of central importance, and you see that you can always compute the basic functionals of the sphere body as polynomial in the radius of the regularizing sphere. And this formula in particular is very important because it is Steiner's formula, and the Steiner formula is very old, much older than the Minkowski theory, and it tells you that essentially for convex bodies you could obtain the surface area of a body by taking the derivative in R of the volume of the sphere body. So this is a very, fruitful idea that tells you that you could define the surface of the boundary of a body as a derivative of the volume of that body in an appropriate sense. And all this comes out of this formula. All right, this the total mean curvature is Minkowski additive, but unfortunately neither the surface area nor the volume are Minkowski additive. And there is an important point which was realized by Minkowski itself, and this, for many applications to entropic forces is really crucial. And Minkowski came out with this idea. Suppose that have an invariant functional, so a functional defined on this class which is invariant under rotation. When I compute this functional on the addition of on the sum of two bodies, B1 and B2, and I freeze one body, and I keep rotating the other body, of course, you can easily see that the functional will change its value. And the question that which seems a kind of idle question, but it is very fruitful, the question he asked was, can I compute the average over all possible orientations of the second body of this functional? It means essentially that I pick up any functional, I compute it on the sum of two, on the addition sum of two bodies, I freeze one body, and I take different orientations of the second body, and at the end of the day, I take an average of all these numbers. This is something that, for example, in computer simulations nowadays is very easy to do. And the question is, what formulae would apply to this average functionals? Can we express these average functionals in terms of fundamental functionals? This was the answer. This was the question, this is the answer, which is remarkable. You see, if you compute the average, in this sense, the isotropic average of the area surface, then this is not additive, unfortunately, but it is given by this formula, which is, of course, asymmetric under the exchange of B1 and B2, and the volume average, which, as you can imagine, plays an important role in the excluded volume computations, can be obtained, the average, the isotropic average of the volume can be obtained by computing these expressions. All right, now there are only 5 or 6 minutes left. Am I right? 4. All right. Well, just an increase of 50%. All right, I don't ask for an increase, but I think that there is a question in your heart at the moment. What has all this to do with excluded volume? Yeah? Because I spoke about this Minkowski wonderful theory. Well, a lot. Oh, this reminds me of a little story I have no time to go into. But this is what you would do in order to construct what we call the excluded body. So this is a given body here. This is another body there. And what you do, you simply take this other body and you slide it onto the other one simply by taking by just sliding the body B2 so that it has a single contact with the body B1, but without rolling it. So this is what you should imagine to do in order to construct the excluded volume. So you take a point C2, for example, which is the centroid of the body B2, and then what you do, you simply come to make the two bodies in contact, and then you slide without rolling this body over the other. And then the excluded region is, for the excluded body, is the one which is bounded by C2. And as we said, we could just take another point inside B2, do the same construction, and it can be proved quite easily that the other body so obtained would be just a translation of the body that I described. So in a way, this construction is obtained to within a translation is obtained by picking up any point in B2, making this smooth contact between the two bodies, moving, sliding one body relative to the other without any relative rotation, and describing the envelope of all trajectories that the point C2 makes in all these possible motions. All right, the important point is that if you just look at this construction, you see that in order to describe in the vector space of the translations this the region which is not accessible to the point C2, you need to add up these two vectors. You know, this is the R1 vector evaluated at this normal. The normal here is outside the boundary of D1. The normal, since the contact is smooth, the normal outside the boundary of V2 is opposite to it. And so you see, in order to reach the point C2 from C1, you first move here with R1, and then you take the opposite of the vector R2 minus nu, because the outer normal at a point of contact to B2 is precisely the opposite to the normal, to the outer normal, to the point where the two bodies are in contact. Well, this is precisely, you see here, this is precisely the Minkowski addition of body 1 with the opposite, the central inverse of body 2. So what we have proved is that the excluded body of B1 and B2, provided they are convex, is the Minkowski sum of body B1 and the inverse, the central inverse of body B2. Now, having made this connection, you can rescue all this wealth of information that the Minkowski theory has provided you with, and you can go and make predictions on the volume excluded by two convex bodies. Because the volume, of course, I just finish here, you can prove something which is intriguing. You can prove that the excluded body of two bodies, B1 and B2, is not symmetric. It is something that at first glance seems to be wrong, but it is a consequence of Minkowski theory. If you take body B1 and body B2 and you compute the excluded body, this is different from the excluded body of the body B2 and the body B1. So it means that the system remembers which body is held fixed and which body goes around it. So the two excluded bodies are not the same, even if the bodies are equal. But, and this is important, they are related via this relationship. If you take the central inverse of the excluded body between B1 and B2, this is the excluded body between B2 and B1. So two excluded bodies are related by this central inverse conjugation, which means that though the excluded body of two bodies is not symmetric, the excluded volume of two bodies is symmetric. So you can, by using this theory, you can speak of the excluded body or volume of two bodies without making any order between the two bodies. And this is the reason why this notion is so important in computing the entropy of systems which have no interaction whatsoever, but the one coming from the exclusion, mutual exclusion of space. The mutual exclusion of space is not symmetric, so should not be called mutual, as done in many books, I'm afraid. But the notion of volume is symmetric. So the excluded volume is symmetric, and you can speak freely of the excluded volume of two bodies. But be careful, never speak about the excluded body of two bodies without specifying the order, because the two bodies are different. I had plenty of examples in which, in the rest of my lecture, which will not be shown, in which I visually indicated how the bodies could be very different from one another, but with the same volume. Thank you very much. I think I overdid a bit.
While the next person is setting up their talk, I'll take one or two questions.
Epifanio, I was intrigued by this formula where you have the expansion in the radius to get the surface measure as you look through. Do you also have this notion of the length of a body? So
well, the length of the body is essentially m.
So that's the Hadwiger measure?
Yes. The length of the body is essentially m, because for a sphere, m is 4 pi r, where r is the radius. And so usually people say that 1/2 m is the length of the body, because it will be 2r for a sphere.
And so a technical problem is one more question. I'm sure help will arrive.
Next question.
All right, yeah, go ahead. Thank you. Oh, yeah, there's a question, right? Sorry.
Just the next question. Is there a direct relationship between your concavity of the body coming from the addition of two convex, or one?
Sorry, coming from?
Coming from the addition of two convex body, or one convex and one concave body, or two concave one?
This is a very good question, but, well, you know the definition of a very good question that I have. As a mathematician, I need a definition for everything. It's a question I don't know the answer to. Yeah, what I'm sure of and what has been proved is that this operation, addition, Minkowski addition, is closed in convex bodies. The point when you add one convex body to a non-convex body, which you can do, you might fall, actually you usually do fall outside the realm of the convex bodies. But it might not be a problem for entropic forces computations because, as I said, the excluded volume is a specific Minkowski addition. And so we do not need all the machinery of convexity. So the message I'm trying to convey is that you might, presumably, develop a theory for excluded bodies also for non-convex shapes.
Well, thank you very much again.
Thank you.